Look down at our planet from orbit, and you see absolute serenity. The clouds drift slowly, the oceans sit undisturbed, and the continents appear perfectly still. But that stillness is an illusion. That satellite hovering above the atmosphere is moving, and so is the massive sphere beneath it. Right now, Earth is hurtling through the vacuum of space at nearly 67,000 miles per hour. Down on the surface, we feel none of this. Local gravity pins us firmly to the ground, allowing towering skyscrapers to stand motionless, and harbors to remain calm, completely masking the violent speed of our cosmic journey. That high-speed journey, our continuous orbit around the sun, is the single mechanism preventing planetary destruction. So consider a thought experiment. What physically happens if that forward orbital velocity instantaneously drops to absolute zero? You wouldn't suddenly be flung eastward into the stratosphere. Earth's rotation on its axis hasn't stopped, and its gravity remains exactly the same. You and the buildings around you would stay firmly planted on the ground. This top-down vector diagram of the inner solar system illustrates the true problem. Normally, our forward momentum creates outward centrifugal force, an inertial force that pushes us away from the center. When that forward momentum disappears, the delicate balance keeping us in orbit is broken. We are left with only one force acting upon us, a massive gravitational pull pointing directly to the sun. Without that curved path, the planet instantly converts from an orbiting body into a falling object. We begin a direct descent toward a star that makes up over 99% of the mass in our solar system. The sudden stop is harmless. The inescapable, immense gravitational trap we have just entered is lethal. We wouldn't instantly hit the sun. We are roughly 93 million miles away, and traversing that much empty space takes time. This data visualization graphs Earth's free fall velocity over time. According to the law of universal gravitation, the physical pull between two objects increases as the distance between them shrinks. So as we get closer to the sun, its gravitational grip compounds exponentially. This compounding force accelerates our descent continuously. What begins as a slow inward drift rapidly steepens into a high-speed terminal plunge. Humanity is trapped on an unavoidable collision course, governed entirely by the unforgiving math of gravity. Back on the ground, the first fatal consequence is thermodynamics. As the distance closes, the sun swells to impossible proportions in the sky, flooding the planet with a massive influx of solar radiation. The oceans absorb the vast majority of this thermal energy. Global water temperatures surge, triggering rapid, large-scale evaporation that spawns catastrophic weather anomalies across every continent. The cryosphere, the frozen regions of our planet, rapidly destabilizes. Massive ice cliffs and polar sheets melt under the immense new thermal load, pouring billions of gallons of fresh water into the swelling, heated seas. Long before we physically reach the star, our shrinking proximity turns our own atmosphere and climate into a lethal oven. In the middle of this descent, an astronomical side question emerges. What happens to the moon? This schematic maps the local gravity well around our planet. The moon's orbit is tied directly to Earth's mass, not directly to the sun's macro-orbit. We operate as a paired system inside this distinct gravity pocket. Because of this localized tether, the moon is dragged along. It continues its monthly cycle, circling a dying planet as both fall uniformly toward the central star. The localized gravity of a small planet offers zero protection against the overwhelming macro-gravitational pull of its host star. In the final days of the descent, the oceans boil completely away. The water vapor forms a suffocating, hyper-pressurized atmosphere over dry, cracked seabeds. At the climax of the fall, the sheer heat and radiation from the approaching corona physically melt the barren crust, reducing rock and stone to a molten sea. A permanent loss of orbit guarantees the total erasure of a planet's surface, biology, and history. Fortunately, that timeline belongs to a thought experiment. Snap back to our current reality, and we find fluffy cumulus clouds, liquid water, and a delicate, thriving atmosphere. The only distinction between a fiery apocalypse and our current habitable paradise is the continuous, unseen speed of our forward movement. We are never truly standing still. Every single second, Earth's cosmic journey actively balances out gravity, pulling us forward just fast enough to avoid falling inward, making life as we know it possible.